Hello, this is exercise 9A for further math students and the statistics part of further maths, obviously. And we're going to do normal hypothesis tests again. And now you might think, oh, I bet we've done this in normal maths. And we have, but there's a subtle difference and a subtle addition to this that we need for further maths. So it's not much difference, but there's a little bit of difference. So let's have a look at it. So this is a starter from A-level maths. It says, it is known that the mean lifetime of a meerkat in the wild is normally distributed, that matters, normally distributed, with a mean 8 and a population variance of 3. A zookeeper thought his meerkats were living longer than this, presumably his meerkats in a zoo. And so he's tested 20 of them. He's got N is 20. And he found that those in the zoos actually were living until they were 9 years old. Okay. Assuming that the standard deviation remains unchanged, test at the 1% significance level whether these results prove that there's evidence that the meerkats in the zoos live longer than those in the wild. Okay, so start off. In the wild, X is normal, 8, 3. He does a sample, X bar, still normal, 8, now what was it? N was 20. So N here is 20. So because of that, we immediately know it reduces the standard deviation now to 3/20. The variance, sorry, to 3/20. H0 is that we believe the mean will be unchanged at 8. And H1 mu is greater than 8. And all you would say here is where mu is the population mean age for the meerkats. And the big question is, I suppose, is are our meerkats living in the zoo from the same population as the original wild ones, or are they somehow different because they live in the zoo? So if we just go on and have a look at that then. So we have said we want to find the probability that X bar is greater than 9, I think it was. And essentially what we're doing is we're saying we've got this normal distribution where we think they should have a mean of 8. But we actually recorded a mean age of 9. And if we find that probability, if it's a very high probability, then we would say, oh, fair enough, it was quite likely to be that high. But if it's a very low probability, then we reject H0. So we type this into our calculator anyway. We go menu 7, normal CD number 2. Lower value is 9, because I can see the lower value of my shaded interval is 9. The upper is infinity, so I type in 9. The sigma is actually the square root of, it was 3 divided by 20, close bracket. And my mu was 8. So when I've done this here, I've got 0.00491. Now this is lower than 1%. It was a one-tailed test 1% level from memory. So this is lower than 1%, so we would say we reject H0. We don't think H0 was right. We have sufficient evidence, and this is the wordy bit that you always have to write, isn't it? It's a bit annoying. I might not bother writing it all down. In fact, I'll just check my answer, see what that said. Sufficient evidence at the 1% significance level that the meerkats in the zoo have a longer lifespan than those in the wild. Right, that makes sense. And everything else there is right. Let's do the difference now. So in the starter, we assumed that the meerkat population was normally distributed. In practice, there are many reasons why you had no idea whether or not they were normal or not. And the great thing about this central limit theorem that we've now seen is you don't have to assume it anymore. As long as your n is bigger than 25, we can basically, we know that the sample distribution becomes normal. And I've written this to be regarded as being normal. I wouldn't suggest to you it's approximately normal. I think the exam wants you to think that it is normal as long as n is big enough. This means that we can basically, even if we're not sure what the underlying distribution is, big samples means we can now do a normal distribution test. So there are 3 things I just want you to be aware of in regard to the variance. You might be told summary statistics in your question, and essentially you can therefore work out the unbiased estimate of of the standard deviation, so, or the variance. So notice what I'm saying here is they may not tell you what the new variance of the new test is, so therefore we have to work it out. But they might tell us the underlying distribution. They might for some reason know what that is, but then we have to use the unbiased estimate and we just adjust it. We've seen this as well. Effectively these are the same, but in one of them they tell me what sigma squared is, and the other one I have to estimate it using the formula. And the third option is they tell me what the population variance is. And if we know the population variance, that's even better than the unbiased estimate. Unbiased estimate is meant to be our best guess of what the variance actually was. Well, if they tell me the population variance is 10, then even better. Now, how do they know it's 10? Well, that's another story, but you know, presumably they've either made it up or they've got some reason to think it's 10. Let's do some questions. But notice in all three cases, the sample mean, whenever I do it, will be basically a normal distribution, and we're going to use sigma squared over n if we know what sigma squared is. I'm not sure if sigma squared is the right thing here. I think I'm basically saying the real population variance or the unbiased. This is meant to be, you know, option 3 here. If I know the actual population variance, sigma squared, and whereas that, I think that's meant to say sigma x squared. You know, somehow you've worked it out. Anyway, so or you've worked out an unbiased estimate, and this is 1 or 2, I suppose, up here. And if you worked out an unbiased estimate, you can use this form. But you'll notice in both cases, you're basically dividing what you've got by n still. So here's my question. We've got a new surgical technique being developed in an attempt to reduce time that patients have to spend in hospital. And in the past, this amount of time, it says, has always been 5.3 days. We do a new sample. That sample has a n is 30. Notice that's bigger than 25. And suddenly it drops down to 5.1 with an unbiased estimate. And I tell you the unbiased estimate is 0.16. Okay then, so let's write all those things down. I'm going to write H0 mu equals, I think it was 5.3. H1, just check the wording, let's go back to it, has reduced, so this is, we think mu is less than 5.3. X was normal, 5.3 comma, and I think they've said it's 0.16. And I'm just going to go x bar actually, and I'm going to divide that by 30. Just check that was the variance, as it was, and n was 30. Perfect. So we've got a normal distribution. We expected it to be 5.3. It was actually 5.1. You can see this is a one-tail test. What was the significance level? 2%. So 2% one-tail. So I'll type this in. So menu 7 again. Normal CD. The lower value is minus 9999. The upper value is 5.1. Sigma is the square root of 0.16 divided by 30. Close bracket. And mu was 5.3. And I get quite a low probability that x bar is lower than 5.1 is 0.003. Now this is lower than 2%. So I'm going to reject H0 and I'm going to basically accept H1 is true. How do I word that? Is that the same? 0.00308. Yeah, I should have written the 308 there, but everything else is right. And this is sufficient evidence at the 2% level that the time spent in hospital has decreased. So that was a proper way of writing it. Just lost a bit of the answer at the bottom. So that's good. So next question. We've got some person, inspector. She seems to be looking at how long it takes. I lost my pen. How long it takes to inspect items being manufactured on an assembly line. And it says it's meant to be 21.75 seconds. But after doing a sample, it goes up to 22.14. And she decided to check whether this new installation of a new lighting system has affected the time. And so she randomly chose 50 of them, and she found that this was true. The sample mean, it says, was 22.14, and the sample variance was 1.6674. First job, calculate an unbiased estimate of the variance, okay, population variance. So just do it here. So we had that the sigma x, the sample squared, was 1.6674. I think I've written that right. Yes, I have, and it was 50. Now remember what you do to get your unbiased estimate. You basically do 50 over 49. It makes it a little bit bigger. Times by the 1.6674. No idea what that's going to give me. 1.6674 times 50 divided by 49. And that gives me 1.701. Okay. So when I come to do part B now, it says x bar is normally distributed. The mean was, let's just see what we got. It was meant to be 21.75. Of course, she got slightly more than that. Hence, I suppose, her theory that it has changed. And 1.701 is the sample variance. We still have to divide that by n. A bit weird. We've kind of done it twice now. We've played around with a 50, but we do have to do it. We think that h0 mu equals 21.75. This lady is not sure how it was going to change initially, so she was saying, how does it change? It's not equal to 21.75. And we know that because here it says, has changed. Oh, it says 5%. It's a two-tailed test, obviously. So this is two-tail, 5%. And that basically means 2.5% each end. There's two ways you can do it. You can either work out what's called a p-value, or you can check it against 5%. We'll probably do both here. So we are going to check the probability that x bar is greater than 21.75, because that's the way our result actually ended up going. So we had an expectation that we'd get 21.75. We actually got, what was it, 22.14. So over here somewhere, 22.14. And the question is that a big enough difference to what we'd have expected? So let's do it. We go menu 7, normal CD, lower is 22.14, upper 99999. Sigma is the square root, what was it? Well, it's 1.701 divided by 50. Okay. And mu was 21.75. What's the probability of that happening? I get 0.0172. Now bear that in mind. You could say this is less than 2.5%. And therefore you would reject, because it's lower, you would reject H0. Or you could work out what's called a p-value. I'll just show you this now on a two-tailed test. You basically, because it's a two-tail, you take the 0.0172 and you double it. What's that? 0.0344, I think. And you compare that to 5%. But either way, you end up with the same result. You reject H0. You need the wordy stuff, I suppose, all that stuff. What have I got here? Well, just about 1.701 is right. That's right. 0.345, the proper rounded version. Oh, I did do the p-value, is less than 5%. We reject H0. Sufficient evidence at the 5% significance level. The population does seem to have changed. So this is our, in class I've got at least one question for you. I've got two questions for you. And then we're going to do exercise 9a. But in my mind, I just want you aware that this whole point of that is, for normal maths, the question has to be normal. And then we can do it. Okay? But for further maths, it doesn't have to be normal. It's any distribution. But n is greater than 25, so therefore by the CLT it becomes normal. But you know what? Other than that, it's basically the same trick, isn't it? You're probably starting to suss that now, that a lot of this is the same as normal maths. And we'll just practice it in class. So we've got two questions to practice in class as at the start of the lesson, and then we can fly into the exercises. Okay, thanks, bye.